For decades, astronomers believed that Jupiter's core was a solid, dense mass, but a discovery suggests this hypothesis is incorrect. What's intriguing is that this not only changes what we believed about Jupiter, but everything we know about gaseous planets in general. Today, the most recent test reveals something that no one expected. Jupiter's core is not solid, nor liquid, nor gaseous. It's something much stranger. What does this mean for our understanding of the planet and the gas giants of the universe? How did Jupiter's core actually form? And how important is it for what we know about our own solar system? Get ready, because let's find out. For a long time, astronomers were torn between two grand hypotheses about how Jupiter formed. The first, known as the gravitational collapse theory, proposed that Jupiter formed directly from the gas in the solar nebula without a solid core. According to this idea, gravity would have collapsed a gigantic cloud of hydrogen and helium, forming the planet in one fell swoop as if it were a failed star. This theory explained very well why Jupiter is so massive and composed mainly of gas. Still, it had a problem. It did not explain how a dense, differentiated internal structure could have formed, a phenomenon that was suspected due to the planet's intense gravitational field. Faced with this hypothesis, another emerged and gained more support over time: the core accretion model. This theory suggests that, like rocky planets, Jupiter began as a solid core, formed by collisions of planetesimals, small bodies of rock and ice orbiting the young sun. As this core grew, its gravity increased, allowing it to attract vast amounts of gas from the surrounding nebula, primarily hydrogen and helium. Thus, a dense core would have formed, surrounded by a huge gaseous envelope. For decades, this vision of a solid core at the heart of Jupiter dominated scientific literature and astronomy books. It was even speculated that such a core could be 10 to 20 times Earth's mass, composed of a mixture of iron, silicates, and carbon compounds. This core was believed to be well differentiated, that is, separated by a clear boundary from the liquid metallic hydrogen envelope, which facilitated calculations of its internal structure and the generation of its magnetic field. However, one detail troubled scientists. These theories were based almost exclusively on models rather than direct observations. No one had ever seen Jupiter's core. Everything we knew about it was deduced from its mass, size, and gravitational effect on other objects. That left open the possibility that the hypotheses were wrong. And then, space missions delivered what astronomers had been asking for: data with which to test those hypotheses. But to everyone's surprise, the information from the space probes not only proved the hypotheses wrong, but also that the core was made of an exotic material. But what was that material? And why does this contradict entirely the theories we had of the formation of Jupiter? The enigma of liquid metallic hydrogen. For many years, Jupiter's solid core theory seemed firm until the data arrived. The first missions to approach Jupiter, such as Voyager in 1979, gathered valuable information about its atmosphere, magnetic field, and size. But it would be the Galileo probe launched by NASA in 1989 that would mark a before and after. Galileo was the first spacecraft to enter orbit around Jupiter, and for more than 7 years, it sent back detailed data on its atmosphere, radiation environment, and composition. But the most intriguing thing arose from indirect measurements of its internal structure. One of the most fascinating findings was the possibility that a highly exotic substance existed in the depths of Jupiter: liquid metallic hydrogen. On our planet, under normal conditions, hydrogen is a gas, but at very high pressures, such as those that exist tens of thousands of miles below Jupiter's surface, its atoms are thought to compress so much that their electrons begin to behave as if they were free, just like in a metal. In this state, hydrogen can conduct electricity and generate magnetic fields, which is crucial to understanding Jupiter's magnetism. Galileo's measurements indicated that a good part of Jupiter's interior could be composed of this strange substance. Here, a profound contradiction arose. If Jupiter's core is completely liquid, composed of metallic hydrogen, how could it have formed in the first place? The accretion model theory indicated that Jupiter must have formed from a solid core that attracted gas. But a liquid core, by definition, cannot serve as a starting point for efficient gravitational accretion. This dilemma posed an original problem. If there was no solid core, then how did Jupiter attract all that gas in its early stage to become what it is today? The scientific community was divided. Some argued that the solid core still existed, but was hidden beneath dense layers of metallic hydrogen, making it impossible to detect accurately. Others began to suggest that the core may have been dissolved or eroded over time, mixing with the surrounding gas. It was a radical idea for the time, but it would prove key in future theories. With all this, it was clear that the probes were revealing a much more complex picture than anyone had anticipated. And then, when it seemed that we could no longer complicate the mystery, a mission came along that would change absolutely everything: Juno. This mission, which aimed to study the gas giant in depth, ended up revealing something extraordinary about its gravitational field, something that would make astronomers and amateurs even more confused. Jupiter not only lacks a clearly defined solid or liquid core, but instead has a diffuse and mixed interior region, something never seen before. How is this possible? The Juno Revolution. When NASA's Juno probe arrived at Jupiter in July of 2016, the goal was clear: to study the planet's atmosphere, magnetic field, and above all, interior with unprecedented precision. Unlike its predecessors, Juno not only orbited the planet, but did so on a highly elliptical polar trajectory that allowed it to come within a mere 2,600 miles of Jupiter's upper clouds in each orbit. From that vantage point, Juno obtained gravitational data with an accuracy never before achieved, and what it revealed was disconcerting. One of the key instruments on board Juno is its Doppler measurement system. This system tracks small changes in the frequency of the radio signal sent between the spacecraft and Earth. When Juno approaches a denser area of Jupiter, its speed is affected by local gravity, and that minuscule change in speed results in a Doppler shift. By carefully analyzing these variations, scientists can infer the distribution of mass in the planet's interior, and what they discovered was surprising. Astronomers knew that if Jupiter had a compact, well-defined core, the gravitational field it would generate would be symmetrical and predictable, like that of a uniform cone. But Juno found the opposite. Jupiter's gravitational field presented undulations as if it were not uniform. What did this mean? In short, it meant that if Jupiter's gravitational field wasn't uniform, it was because the mass of its core wasn't either. The variations detected by Juno could not be explained with a solid core as previously believed. Moreover, models that tried to simulate Jupiter's gravitational field failed again and again, unless they included a new idea: that the planet's core wasn't a core at all, at least not in the traditional sense. This is where the concept of a fuzzy core or dilute core emerged, a region in Jupiter's interior in which heavy materials, rock, ice, metals, are not confined to a compact sphere, but are gradually mixed with the liquid metallic hydrogen that surrounds them. Instead of a clear boundary between the core and the envelope, there would be a smooth transition in which heavy elements float in varying concentrations over thousands of miles. This model explained the gravitational anomalies observed by Juno and also offered an alternative solution to the metallic hydrogen mystery. Perhaps the core never fully consolidated, but remained a mixture in different proportions. This finding shook the foundations of planetary theory, but it also opened a new question: how does such a nucleus form? The answers would be so challenging that astronomers would have no choice but to develop a new theory to explain how Jupiter became the largest planet. The new theory: had an object hit Jupiter? Once the possibility that Jupiter's core was not compact but diffuse was accepted, the next big question was inevitable: how does something like this form? For years, many scientists championed a spectacular but logical idea. In the early solar system, a massive object, possibly a rocky planet the size of Earth, may have collided with the young Jupiter. This impact, energetic enough, would have destabilized its initial core and violently mixed it with the hydrogen and helium in the outer layers, diluting it in the process. The idea of impact was tempting. Not only did it explain the diffusion of the core, but it also fit with what we know about the violence of planetary formation. After all, similar events could have caused Uranus's extreme tilt or the Moon's birth from a collision between Earth and an object the size of Mars. But numerical models and high-resolution simulations began to tell another story. In several recent studies, such as those of Simon Mueller's team from the Center of Theoretical Astrophysics and Cosmology at the University of Zurich, they tried to replicate such a collision on supercomputers, adjusting all kinds of parameters: size of the impactor, angle of collision, composition of the materials, density of Jupiter at that time. The result was always the same. In each simulation, after the initial chaos, the heavier materials in the core tended to recompact and separate from the gas envelope. That is, the nucleus was recomposed into a well-defined sphere, not into a diffuse structure as Juno observes. This finding sparked a new, even more intriguing hypothesis. Perhaps Jupiter's core was never compact. Perhaps, early on, the planet began to form through the simultaneous accumulation of heavy materials and light gas. That is, instead of a two-stage process, first rock then gas, accretion would have occurred in a mixed way. In that scenario, planetesimals laden with rock and ice mixed with hydrogen and helium as the planet grew, creating a natural compositional gradient that never quite separated. Over time, internal processes such as convection, turbulence, and thermal diffusion would have maintained that mixture without allowing heavier materials to sink completely. But there was a problem. Calculations indicate that under the extreme conditions of the Jovian interior, convection should thoroughly mix the materials, homogenizing the composition. For a fuzzy core to remain stable for billions of years, there must be additional mechanisms, such as no convection zones or precise thermal gradients that slow down complete mixing. The problem is that until now, neither of these two mechanisms had ever been found present in Jupiter, or so we thought. Unexpectedly, the clue needed to understand Jupiter's core would not come from Jupiter, but from a much farther place. Hidden in Saturn's rings, scientists found the last piece of the puzzle of this mystery. But what exactly did they find? How can Saturn's rings be related to Jupiter's core? Ring seismology and Jupiter's best-kept secret. Thanks to the Cassini mission, which orbited Saturn between 2004 and 2017, astronomers began to apply an innovative technique known as ring seismology. This technique consists of observing the waves that propagate in the planet's rings, caused by internal oscillations in their structure. Those oscillations, like earthquakes on Earth, reveal hidden details about its interior. In 2021, a group of scientists led by Christopher Mankiewicz and Mark Marley published a study in the journal Nature Astronomy with a crucial finding. Saturn also has a fuzzy core, just as suspected on Jupiter. But in this case, the evidence was even more conclusive. The waves in Saturn's rings showed behavior that could only be explained if the planet's core was not a compact sphere, but a large mixed region extending up to 60% of the planet's radius. Instead of a defined core, there is a progressive transition between the heavy materials and the gaseous envelope. This discovery was a bombshell in the scientific community. If both Jupiter and Saturn have fuzzy cores, then this is probably not an exception, but a rule. This implies that classical models of planet formation need a profound revision. The idea that gas giants form in two phases, first a solid core, then a rapid accretion of gas, could be incorrect. In addition, in recent years, we have detected thousands of exoplanets, many of them gas giants the size of Jupiter or Saturn. If fuzzy nuclei are ordinary, it is likely that many of these worlds also have completely different internal structures than we had imagined. Density, mass distribution, thermal dynamics, the formation of magnetic fields, and even the way the planets in our solar system were formed all must be reconsidered in light of this new reality. And speaking of magnetic fields, Juno's data also revealed puzzling behavior in Jupiter's magnetic field. Even though we know that it is generated by the dynamo effect of liquid metallic hydrogen, the regions where that effect should be most substantial do not quite align with the observations. Non-convective areas have been detected where the material does not circulate as expected, which further complicates the explanation. All of this suggests that there are still mechanisms we don't fully understand. The combination of fuzzy cores, non-convective zones, and irregular magnetic fields opens a new frontier in planetary physics. What started as a simple question about what's at the center of Jupiter ended up completely destabilizing what we thought we knew about how worlds are born throughout the galaxy. What other mysteries does the largest planet of all hide from us? If you'd like to learn more about Jupiter, check out these 10 mind-blowing facts about it.